Hello, students. We left off last time with a discussion of some basics of objects that move in circles. And in particular, we talked about things like the fact that an object moving in a circle, even if it's moving at a constant speed, is always accelerating. Notice I didn't say constant velocity, right? In order for velocity to be constant, an object has to move in a straight line at a constant speed. So even if something moves in a straight line, scratch that, even if something moves at a constant speed, if it's not moving in a straight line, it is changing velocity and therefore accelerating. Obviously, an object moving in a circle is constantly changing direction and thus is constantly accelerating. And we said, okay, so at what rate does an object moving in a circle accelerate? We derived an expression for that. Then we could say, what's the net force on something moving in a circle? We derived an expression for that. I will urge you to go back to lesson 1 if you need a recap on that stuff. We left off saying, hey, you know, this idea of centripetal force, it's not a different kind of force. It's that any of the forces we already know about, or sometimes some of those forces, can act as a centripetal force. And what that means is one of those forces might be a force that always points towards the center of a circular path. That's the criteria for a force being a centripetal force. So we're going to talk about 4 of our 5 forces that are pretty good common representations of situations where objects move in circles, right? And pretty good, 4 of these forces are pretty good examples of centripetal forces in some situations. And so the first one of them is weight, right? Our 5 forces are, we call them WANTF for weight, applied, normal, tension, and friction. And I'm going to start by saying that there's a pretty darn good case for an object's weight acting as a centripetal force. And what that means is, okay, well, here's a path that something moves in. Here's the thing, the object moving in a circle, and what we're saying is there's a force, mg, that acts towards the center of a path. Well, when does that happen? Well, that happens for an object in orbit. Exclamation point is optional. So what we would say here is we would say, if we were writing what we can call a net FC statement, we would say mg equals mac, or mg is mv squared over r. And you can actually tell right now that m's would go away and there's problems you can solve. All right, you can see the beginnings of a solution for something. Okay? The more important part right now is you can understand that when an object is in orbit around another object, right, here's, you know, say maybe this is the green thing's the Earth and the red thing's the moon, or the green thing's the Earth and the red thing's a satellite, or the green thing's the sun and the red thing's a planet, right? It's the force of gravitational attraction that the center object exerts on the orbiting object that makes the orbiter move in a circle. Right? That gravitational force always is attractive and points towards the center of the orbiting object's circular path. Thus, it's a centripetal force. And thus, when we write our net FC statement, well, that's the only force that there is. Okay? So weight is a great example, or gravitational force, of an object moving in a circle because of a certain kind of force. I'll go to normal now. Well, I'll go to friction. How about I go to friction? Friction is a very common example. Again, I mean, I don't know, we can draw my same thing. Here's an object's path. Here's the object, I don't know, right here. And it might be hard to imagine, you know, when is this happening, that it's friction that points towards the center? But what you can ask yourself here is, what's a situation in which, if there weren't friction, then an object couldn't keep moving in a circle or moving around a circle? And if you think about that, the answer can become clear that a car on a curve, exclamation point again, okay, well, cars are able to go around turns because of friction that road exerts on tires. All right, cars are able to do anything they do because of friction that road exerts on tires. In this case, well, if there is no friction between road and tires, then cars can't turn. All right, so that leads to the justification that the only reason that a car can make it around a turn is because of friction. All right, so friction will act as a centripetal force for a car going around a curve. So we could do our, all right, well that means that net FC statement says the friction force equals MAC, or the friction force equals MV squared over R. You might be able to imagine, oh wait, there's other ways I can express friction force too, and that gets us into some more complicated problem solving. All right, but you have to be able to recognize for a car going around a curve, the reason it's able to do that is because friction allows it to do so. Thus, friction is the centripetal force. Thus, when we write our net FC statement, it's friction force equals MAC. All right. Example 3. I jumped right to the end there. Well, tension is a pretty popular one. Do I have to draw this again? Sure, why not? Here's an object moving around in a here's an object moving around in a circle because there's a... Now, I should say this. There's no requirement that says that when I draw this vector, it has to end at the middle of the circle. I mean, it's okay to draw the, you know, if that's the, if right here is the center of the circle, as long as our force points towards that place and through it is okay, that's a reasonable representation of a centripetal force. It's not the most common that you'll see. You usually, I mean, maybe we do this. Let me write that as T. It's just worth mentioning that we don't have to, it's not like the centripetal force has to end at the center of the circle. There's no requirement of that. All right, so when is it that an object can move in a circle because of a tension force? Well, that must mean that there's a rope or a chain or a cable attached to an object that's moving in a circle. And that happens in a lot of cases. I mean, how common are they? I mean, one that is pretty darn common is a swing set. All right. Now, a swing set doesn't always move in a full circle, but when we have a chain like this, and here's the seat, and this thing can move at least in part of a circular path back and forth, the tension force is the force that's always pointing towards the center. All right, you're going to have mg like this and tension like this. In different places, well, mg will always be the same size and always point straight down. Tension will always, actually won't always be the same size, but it will always point toward the center. Now that's a little bit of a different situation because there's some more complex problem solving to do there. So what I want to stick to is things that move in horizontal circles because of tension, and that's, you know, like you got your tether ball. You ever, you know the tether ball game there. You got what else do you got? You got your classic ball on the end of a string. How often does that really happen? But it happens, sure. How about this? We'll just write ball on string. Ball on string. Now, in many cases, this gets simplified to imagine that, watch, if we look like this, here's a sort of end-on view of the path. We will simplify to say, here's the object, and it's the tension that points straight in. The tension can't point straight in because there is a gravitational force downward on this thing. So there actually has to be some component of tension that points upward to be equal and opposite to gravitational force. So there actually would be a force like this, a component of tension. So the whole tension would have to point upward a little bit. In a lot of cases, we simplify or maybe we usually say this angle's really small, and thus this tension and this component of tension, the centripetal component of tension, are just about the same thing. So in lots of cases here, we would say T is MAC. All right, when we're specifically given that, oh, there's an angle here, then that means we have to start thinking about components, but we'll get to that sort of situation. In the simplest one, though, we can simplify to say, okay, if there's a rope attached to this thing, then there's a component. I'm going to write this. There's a component, a centripetal component of tension for sure, that is the reason the object moves in a circle. Okay, and then the last one, normal. This happens quite a bit, really. So imagine that it's contact with a surface that allows you to move in a circle. And I hear you saying, I mean, this is contact with a surface. Yeah, except normal forces always point perpendicular to the surface. So we need something where perpendicular to a surface always points inward. All right, and there's a couple of those. The big one you can imagine is, imagine this. Imagine you got a, all right, you got an old kind of washing machine where you load it from the top. I know all you fancy people got your front loaders now. I got a front loader myself. But if you have an old one with a drum in it, it's called, I think it's still called a drum regardless. But if you load from the top, then the walls are, there's a cylinder here. All right, and you got your spin cycle, right? You know the spin cycle at the end when you're getting all the excess water out of there? Here's a sock. And that sock moves around in a path like this, jammed against the wall. And the reason that sock moves in a circular path is because, well, the wall is there, exerting a force inward towards the center of that circular path. All right, there are amusement parks aplenty like that. Amusement park rides, I should say, aplenty like that. All right, there's lots of them where you stand against the wall of a big cylinder, and then the thing spins, and you have the time of your life. All right, so fine. When we say net FC here, we would say the normal force equals MAC. The normal force is MV squared over R. Good? Fine? What about applied force? How come we didn't say that? Well, it's not very common that something moves in a circle because you are constantly, I mean, like imagine you yourself keep pushing something with your hands towards the center of its path. That just doesn't really happen. You'd have to say like, here's an object and it's moving this way, and you go, okay, as it's right there, I'll push it with my hands like this, okay, and then the thing gets to here, and now it's moving this way, and you have to move yourself over to here and keep pushing, and then it's over here, and it's moving this way, and you say, okay, I'll keep pushing it. That's not real common, okay? Now, what we don't mean by this is like, this doesn't mean like, you know, making a bicycle wheel turn. First of all, a bicycle wheel rotates. It's not a thing that moves in a circular path. All right, you might say, what about like the pedals on a bicycle? That makes the wheel turn. That's something different. All right, that's not you. You know, the wheel does this, sure, because there's a chain attached to this thing, and well, that's because of like forces like that. That's a whole different phenomenon. It has to do with what's called torque. All right, so we think a lot less in this part of the unit about things that rotate than we do things that move in a path that's a circle. All right, and applied force is just pretty rare. Fair enough. Okay, fine. Okay, here's a couple of solved examples. This one is what's called a it just deals with algebraic relationships. All right, it says you got a ball on the end of a string swung at a certain speed, and okay, and that requires a certain force F. All right, so all we can say about F is that it's equal to that, We don't know what m is, we don't know what v is, we don't know what r is, but some force F makes something move in a circle. All right. Now, scenario says suddenly we increase the ball's velocity by a factor of 4 and we double the radius of the circular path, but apparently we keep the same object. All right, so let's call this like F1 and V1 and R1 and M1. All right, and then we look at a different scenario that's described. We can say F2. Well, we still use the same object, M1. But now we have velocities increased by a factor of 4. So watch this. We got to say this is now 4 v1, and we square that, and divided by 2 r1, right? Doubles the radius. Velocity by a factor of 4. All right, so what's F2? How much force is required now? And we're going to answer in terms of F. So F2 is, well, this 4 squared gives me 16 m1 v1 over 2r1. F2 equals 8 m1 v1, oops, over r, right? If I square 4v, I get 16v squared, right? I got to square that. Okay, so check it out. This part is this. So this says, by making the adjustments we've made, F2 is 8 times F1. Fair enough? It's okay? What you should be able to recognize is, if you change v by some factor, then F changes by the square of that factor. F, V. F is proportional to V squared. That's a quadratic graph. All right? F. R is an inverse, so this does, as one gets bigger, other gets smaller by the same factor. If R gets twice as big, F gets twice as small. If R gets 1/3 as big, F gets 3 times as big. Okay? And this question combines two of those scenarios into one. Okay? Okay, so we got a kid on the rim of a merry-go-round moving at that speed. What's the child's centripetal acceleration? You must know that AC can be written a couple of ways, but this is the easiest way to do it. And we get 6 meters per second over 3 meters. It's 36 over 3. Oh, this is 12 meters per second per second. What's the minimum force between her feet and the floor to keep her from slipping? Okay, this is a kid standing on a rotating platform. All right, here's the kid. Well, here's the kids on the rim. Fine, kids on the edge. Here's the kid, and the kid moves in a circle because of a force that points inward, and that force is a friction force. It doesn't say the kid's holding onto a pole. It doesn't say there's ropes attached to the kid. It's definitely not the kid's weight that points towards the center of this rotating disc. So when we write our net FC, we're saying that friction force is the centripetal force, is MAC. And we already have AC. The friction force is the kid's mass, 50 times 12. That's 600 newtons. Now, for this kid not to slip, we could now talk about the coefficient of friction that's required to keep this kid from slipping, right? Mu static is force of friction max, static max, over n, right? Minimum coefficient of friction, just keep the kid from slipping, right? That means we can use, right? We can only use friction force is mu n when we are at the maximum peak. amount of static friction force, and we've qualified that by saying just about to slip. All right, so let's see, what's our, this is, well, check this out, right? Here's normal, here's mg, so this is FFS max over mg, which is 600 newtons over mg, 500 newtons. That's 1.2. Uh-oh. Notice this part of the question. In other words, is this person, is she likely to stay in the merry-go-round? No, not likely. Why is that? Because mu static is very rarely more than 1. This is an infeasible situation. Good to be able to recognize. Okay? Okay. Yeah, okay, so this is a more challenge. Well, it's kind of like this question. The friction ones are neat questions because you can, I mean, we kind of did all that right here, but we're going to do it again as a single question. All right, there's a cop car driving around a circular curve at a maximum speed without slipping. Ooh, that means we're talking about, we're saying we're at FFS max. What's the coefficient of static friction? So here is a section of the curve. Here's the car. Car's got a gravitational force mg acting on it, a normal force, and here's a friction force pointing towards the center of the curve. All right, watch what we can do. There's 2 dimensions that we're concerned with. And the one question that we always raise when we're doing dynamics problems is, what axes should I be dealing with? Well, one axis has to be the direction that an object accelerates, and this object accelerates towards the center, so therefore our axes are the centripetal and then perpendicular to that. Oh, good. All right, those are directions that our forces already point in. So when we say net Fc, we say friction force is MAC, or friction force is mv squared over r. Now we're looking for a coefficient of friction. Luckily, we've qualified that this static, or this friction force, is a max static friction. So it's okay to say that this is mu static times the normal force. Right? A net Fy will tell us that n minus mg is may, not accelerating in the vertical direction. And this mg can go in there. When we get mu static mg is mv squared over r. And here's what doesn't matter. It doesn't matter how massive the car is. The coefficient of static friction we can now solve for. Mu s is v squared over gr. And I don't care what the actual number is. That's the solution. Okay? So, neat questions will do more than just say, how big is the force pointing towards the middle? All right? More challenging questions will present you with the scenario that you have to interpret first of all and say, what is that force that points towards the center? Maybe what do I have to do to manipulate and relate things I know about that force, and then especially then look in the other perpendicular dimension and say, what else can I figure out? And okay? So you just have to remember that a lot of people will write this and say, but it doesn't say mass in this, it doesn't tell me what the mass is, so I will just stop working. Don't do that. Keep going. All right? Keep going. Do the physics. Okay? All right. Farewell.